Hi everyone, I hope you are doing well. So in today's video, I'll be going through the 2018 chemistry exam multiple choice section. Like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. And yeah guys, let's smash through this video. Question 1. Which of the following statement is most correct? So most accurate? All fuel cells are galvanic cells. Yes, we can consider that to be right, because remember, fuel cells, what they do, what's the main purpose of fuel cells is they convert chemical energy to electrical energy, which is the same function as a galvanic cell, so I would say I'll put a tick there. I want to look at the other answers to see maybe one's better than that. So remember, we're talking about most correct. So all galvanic cells are primary cells. No, that's rubbish, because we know some galvanic cells are secondary cells. Primary cells are the ones that can only discharge and it cannot be recharged. But we know some galvanic cells can actually be secondary cells and they can be recharged. So not all galvanic cells are primary cells. They could also be secondary cells. C, all secondary cells have porous electrodes. No, that's exaggerating everything. So there are some secondary cells that don't actually have porous electrodes. They could have solid electrodes. So that's just over exaggerating. So I wouldn't say C. D, all fuel cells are more efficient than all secondary cells. Okay, this is also exaggerating. You're saying all secondary cells. Remember, secondary cells are the ones that are that can be recharged. I think, especially in this future, there are some secondary cells that could be much more efficient than fuel cells. So I think D wouldn't be the best. If they said all fuel cells are more efficient than all, let's say, galvanic cells, I would say true, but when they're saying all secondary cells, you remember secondary cells tend to be quite efficient because they can be recharged. So I would say D is wrong. I think there are some secondary cells that are better than fuel cells. So in terms of this, the most correct I would say is A. I hope that's right, yeah. Question 2. Aspartame is a widely used sweetener. Aspartame is what? So it contains a glycosidic linkage. Let's check that. Let's go to our data book. Let's scroll down. Where's aspartame? I call it aspartame, but here is aspartame. Okay, what can we see? So does it contain a glycosidic linkage? Remember, what is a glycosidic linkage? It looks like this. It has an O. Oops. So it has like an O, and it has this kind of, this is how it looks like. So if you look over here, in terms of cellulose, there is a glycosidic linkage. This is how it's supposed to look like, a glycosidic linkage. Is there a glycosidic linkage in this one? Look, many students would say this is a glycosidic linkage. Be careful, that's not true. Remember, this is an ester group. Look at this. This is an ester group. It's not a glycosidic linkage. So I would say, there is no glycosidic linkage in aspartame. Is a naturally occurring sugar? No, aspartame is a sweetener. So it's not a naturally occurring sugar. Has an energy content similar to that of sucrose? That's true. You should know that. Remember that the energy content of sucrose, which I think is around 16 kilojoules per gram, whereas I think, if I'm not mistaken, aspartame is around 16.1. So they are very similar. There's, the energy content is similar, but the difference is that aspartame is 100 or 200 times sweetener. It's sweeter than normal sucrose or sugar. So that's why, in example, those who are doing dieting, they eat less, so they can eat 1 gram of sucrose, which is sugar, or they can eat 1 gram of aspartame. The good thing about aspartame, it's a natural, it's a, what we call a artificial sweetener. If you eat 1 gram, what do we know? It gives the same energy as sucrose, but guess what? It's much sweetener. So most of people will actually put less than 1 gram. They could put maybe, I don't know, maybe 0.1 gram, which will be the same flavor, same sweetness as sucrose with 1 gram. So it's better because it kind of is less energy in a way that you would want to eat less of it because it's much sweeter. So it does have the same energy content similar to that of sucrose. So that is true. So I would say C is right. And what about the last one? Contains 2 amino groups in its chemical structure. Let's check. Well, there is an amine group here. That's great. Be careful, this is not an amine group. This is an amide. is an amide group. So there's only one amide, not two. So I would say only C is your answer. Not too bad. So, all right, next question. Which of the following statement about fuel is correct? Petroleum gas is a form of a renewable energy. Absolutely, that's rubbish. It is non-renewable. It's a fossil fuel. So, electricity can only be generated by burning coal. No. Like, remember, okay, coal is the most, like, electricity is mostly generated by coal, but not like, there could be other ways you can actually generate electricity. So it's not only coal. So yeah, that's just too much when they're saying electricity can only be generated by coal. There are many ways you can actually produce energy. Like, for example, hydropower. Yeah, you can, there's many ways. What about this? C, carbon dioxide is not produced when biogas is burned. No, false. Remember, biogas is mostly methane and carbon dioxide. So carbon dioxide is pretty much produced when it is burnt. So wrong. Be careful with that. A lot of students might think, oh, biogas is a biofuel, so it doesn't have any, greenhouse gases such as carbon dioxide. Believe me, so be careful. It has carbon dioxide. D says biodiesel can be derived from both plant and animal material. Absolutely. D is beautiful. That's it. Next question. At a molecular level, protein P is shaped like a coil. So it's a protein and it's shaped like a coil. When a solution of protein P is mixed with citric acid, so you know what citric acid is, it has a low pH. Remember, it's acid, so the pH is very low. Solid lumps form. The change in the structure of protein B is due to what? So imagine, okay, so so initially it was shaped as a coil. So imagine this is how it looks. This is protein P. And then after, mixing it with citric acid, what happens is it forms lumps. So imagine like it goes like that. It forms these lumps. Okay, now what's happened? Well, you straight away know it's a protein. And what happens when there is a change in pH or temperature? Denaturation occurs. So this will, be likely due to denaturation. Let's look at A. It says hydrolysis. No, hydrolysis is the breakdown of pretty much the primary structure. You remember, it's the polypeptides. You break them down. It's not happening here. Remember, the primary structure is still normal, whereas the secondary, tertiary, or the quaternary are kind of disrupted in this case. So A is wrong. Denaturation, most likely, I would say that. Polymerization, no, that's absolute rubbish. D, the formation of polypeptide bonds, no, that's not right. So it can only be B. I would say B is the best answer for this kind of question. Question 5. Coal seam gas is used to generate electricity. In other words, you've just answered the question that was in question 3. There's other ways you can generate electricity. Which of the following statements applies to coal seam gas? Coal seam gas is mostly methane. That's true. And it is found naturally in commercial quantities near some coal deposits. That's where they find it. True. Remember, it's coal. The name comes from coal. It's the gas is taken from coal. So, pretty much 5 looks very good. So put a tick on that. B, burning coal produces less greenhouse emissions by mass than burning coal seam gas. Rubbish. C, water released during the extraction of coal seam gas is used to irrigate farms. I wouldn't say that's the best thing to do. I mean, like, if you're taking water that is released, let's say, in the extraction of coal seam, there's going to be impurities. You're taking it from coal. There's going to be sulfur, sulfur. There's going to be nitrogen. There's going to be these impurities. And if you're going to irrigate farms, use it for farming, it's not going to be great for farming. It's not, yeah. So I wouldn't say that's what happens. So I would say C is wrong. Coal seam gas is extracted from decomposing plant and animal rubbish. Decomposing of plant and animal material would have been like a for example, biodiesel. So coal seam gas is non-renewable, so it's not taken from these. So question 5A would be the most suitable. Question 6. Ethoxyethane. This is commonly used as a solvent in the purifications of compounds. The boiling point of this is 36. Okay, so it's 36 degrees. The safety data sheet for this states that it's extremely flammable. Okay, keep away from sources of ignition. During the purification process, a compound is dissolved in this by heating it for an extended period of time. This is done using glassware that is open to the atmosphere. This step in the purification process should be carried out using a what? Let's see, water bath. That's safe because, like, imagine like bathing in water. You're not, having a source of ignition. So, in a fume hood, yes, a fume hood is great because of ventilation. So, not all, like, for example, let's say a source of ignition from like gases come, and like a fume hood would ventilate that, and when like no source of ignition would happen. So a fume hood is, I think, great in this. Water bath, yes. On a laboratory bench, no. Laboratory bench, not the best thing to do. A Bunsen burner, no way. A Bunsen burner is a source of ignition, by the way. It creates a source of ignition. So anything with a Bunsen burner, so C and D, would absolutely be wrong in that case. So yeah, a water bath in a fume cupboard is the most appropriate in this case because fume cupboard sucks in all that like ventilation in a way, like sucks all those gases that or vapor. I meant vapor. It sucks those vapors that can create any source of ignition. So yeah. Question 7. Vitamins are required by the human body. Okay. Which of the following statements about vitamins is correct? Vitamin D2 and vitamin D3 are structural isomers. Let's check that using our formula sheet. So here's vitamin 2 and vitamin D3. What can we see? Well, the only difference is this. Look at this. This one has a double bond here, and it has this. Whereas this one over here has no double bond, but it's shorter. Have a look at that. My apologies. So this one has this, whereas this has 5 carbons in this case, whereas this one has 4. Now, what do we know about these? Well, then it cannot be structural isomers. Remember, structural isomers have the same molecular formula. Whereas this actually, in this case, this has more carbons than this one. So absolutely, that's not true. So I want to say is wrong. Vitamin D can be stored in the fatty tissue of the body. So we know fatty tissue is what? Like fatty tissue is, we call it adipose in a way. So fatty tissue is adipose, and adipose is non-polar. Like it's fat. And it doesn't like water. So because vitamin D, most of it, if you look at this, most of the structure is what? It is non-polar, and we only have this OH group that is this small polar group. But overall, the overall structure is non-polar. So I think it's absolutely, vitamin can be stored in fatty tissues because, that could be true. So I'm going to put a tick on that. It can be stored in fatty tissues. Vitamin D is a water soluble? No. It's not water soluble, as you can see. It has a very high non-polar group, this whole non-polar part. So C is wrong. Vitamin D is essential in the human diet as it cannot be manufactured by the body. Wrong. Remember, vitamin D is non-essential. You can take it from the sun. Vitamin C, whenever you're talking about vitamin C, that is essential because you need to consume it. So the only possible answer would be B. Vitamin D can be stored in the fatty tissues of the body. Yeah, it's fatty tissue is non-polar, by the way. So fatty tissue is like, fat. So fats, there's no water in there. So, so fatty tissues are non-polar. So it would, because vitamin D is non-polar, it would likely to be stored in that fatty tissue. Question 8. Which of the following fatty acids is an omega-3 fatty acids? Nice and easy. Let's use our data sheet again. So, let's check the first one. If I go to here, arachidonic, I don't know how to say that, but it's right over here. The way we check it is, let's count the carbons until we hit the double bond. So if we start here, that's 1 carbon. Plus, there's now 4, so now there's total 5 because this one has 4 in here. So now we have 5, and then 6. That's where the double bond occurs. So this one would be an omega-6, not an omega-3. So next one is what? Palmitoleic. This one. So it has 1. That's plus 4. So that's 5, 6, 7. So this is like an omega-7. So B is wrong. It's not omega-3. Linolenic. So linolenic, which is this one over here. So it has 1, 2, and 3. Omega 3 is this one. Beautiful. C. Yeah. That is that. And the other one is rubbish because linear here, that's 1, that's 4, so 5, and that's 6. So this one here also is an omega 6, so not omega. So it's your only answer is for A is C. Question 9. When molten sodium chloride, NaCl, is electrolyzed, the product formed at the cathode. So the cathode is where, what do we know, is reduction is going to occur. So we're using molten, so we're going to have sodium chloride. So let's go to our formula sheet and see what's going to happen using our electrochemical series. So we have sodium chloride. So remember, it's going to be this sodium over here. When molten sodium, so and chloride. Where is chlorine? That's on top. Where is it? It's this one. So what can we see? Remember, on the left, on this here, on the left is where reduction is going to happen. So yeah. And it's like the highest one, where the, yeah. Whereas, what did I just do? Yep, and on this side is where oxidation happens, where it's mostly at the bottom. So, for example, what is the highest in terms of, like in terms of on the left? Well, this one's the highest on the left, as you can see. So this one is is going to be reduced, and it's our strongest oxidant. So because this is going to be reduced, remember, cathode is where reduction occurs. So imagine this is going to go this way. So it's going to become Na plus aqueous plus electrons goes to Na solid. That's what's going to occur at the, the cathode. Yeah, so sodium liquid. Yeah, it will be liquid in this case because it's molten. So, yeah, sodium liquid will be the byproduct that will form at the cathode. Easy. Next question. Bioethanol, this is produced by the fermentation of glucose according to this following equation. So we have that glucose ferments to ethanol, bioethanol, and carbon dioxide. So the mass of ethanol obtained when 5.68 grams of carbon dioxide CO2 is produced is what? A beautiful stoichiometric question. So very easy. So if we know the mass of CO2 is 5.68 grams, we want to find the mole of it. So CO2 is going to be 5.68 divided by the molar mass of CO2, which is what? Well, we know carbon's 12, plus there's 2 oxygens, so 16 times 2. And that's going to give us what? 5.68, 12, 16 times 2. That is going to be 0.129 mole. And so we're going to use, of course, ratios. So if I want to find the mole of C2H5OH, so the ethanol, so I'm going to use that 0.129. And on times of what do I want to find out? Well, I want to find the mole of this one over here. What is the coefficient? It's 2. Divided by which one did I just use? Like, for example, the mole of CO2 to calculate that, which has a mole of 2. So it's a 1-to-1 ratio. So we can just write that as times as a 1. So it's just going to be the same. Mole. Now, lastly, we just want to find the mass. So remember, just like, so to find the mass, it's much easier. So let me just rub quite everything out. Bring this up here. So to find the mass of that, this is going to be 0.129, the mole, times the molar mass. In this case, the molar mass of this is how many carbons? So we have 2 times 12 plus how many hydrogens, which is 6, plus 16. So let's do that. Alright, so 6 plus 16. And that's going to give us 5.94. So question 10D. Easy. A galvanic cell is set up as shown in the diagram below. Alright, what can we see? Well, we have a cell bridge, we have iron electrode and silver. I think Ag is silver, yeah. When the cell's operating, A gas forms at the electrode. Okay, the way we do this question is, let's go to our electrochemical series, and that's going to predict everything for us. So, all right. In this case, we have iron. Where's iron? So iron's over here. And we have Ag. So where is Ag? It's right over here. Now, of course, what's going to react, like the strongest reduced, or the oxidant is going to go upwards. It's going to be this one, Ag plus. So it's going to be, this one that goes this way. So we're going to form some Ag solid in this reaction. And well, this one is the strongest oxidation one, so it's strongest reductant, and it's going to go this way. So we're going to also produce some pretty much Fe2 plus ions. Yeah, that's pretty much the hint I can do for this one. Okay, wait. Well, I'm not, okay, so yeah. I just want to make sure 100%. Let's also like label. So, okay, Ag is the strongest, so it's going to be positive. So Ag is going to be a positive because it's the highest one. So, this one's going to be positive and this one's going to be negative. So the electrons are going to go from negative to positive in a galvanic cell, and that's it. So when the cell is operating, a gas forms at the Ag electrode. There is no gas that's being produced, so absolutely not. B, the mass of Ag electrode increases. Do you know how I always, like, the easiest way that I know which mass increases? This is how. So imagine how think of the electron flow. If the electron flow is going to the Ag electrode, imagine mass is coming to it and it's being put in here, whereas this one's losing mass here. Imagine the mass here is losing, whereas the electrons are gonna pretty much putting it all over here. So the flow of electron tells us where pretty much the mass is being put, which mass of the electrode increases, which in this case, yes, the mass of Ag increases. As you can see, the electrons are going, the direction are going to their Ag electrode. So I would say that is a true statement, so I'm going to put a tick there. Ag plus ions move towards the Fe electrodes, rubbish. And D, electrons move from the Ag to the Fe electrode. No, they move from the Fe electrode to the Ag. So B is your answer for that one. Nice. Question 12, the overall reaction for an acidic fuel cell is shown. Okay, so we can see hydrogen gas, we know an oxygen gas, and they're producing water. Now you should straight away know that when oxygen reacts in a fuel cell, that's always going to be occurring at the cathode, and this one here is going to be the anode, which is our fuel in this case. Porous electrodes are often used in acidic fuel cells because what? They are highly reactive? No. Porous electrodes are used because they are not reactive. Be careful. Are cheap to produce and readily available? I wouldn't say they're cheap because porous electrodes are made from nanomaterial, and they're very expensive nanomaterial. So yeah, and I think, remember, porous material is what? It's like material that has holes, little holes, very small nano holes that let ions and other stuff inside. So I don't think they're cheap, because the fuel cells tend to be very expensive. So I wouldn't say that's right. Are more efficient than solid electrodes at moving charges and reactants? True, yes. They're much efficient in moving charges because remember, there's those little holes and they can easily let those charges move. And also for reactants. So I'll say that's great. D, provide a surface for the hydrogen and oxygen to directly react together. Be careful with the wording here. Directly react together. They cannot directly react together because if that happens, what happens? It's not a fuel cell anymore. Remember, a fuel cell, what it does, it converts chemical energy to electricity. So if oxygen and hydrogen pretty much react, it's going to be chemical energy to thermal energy, because all that is, it's going to create a spontaneous reaction that just creates heat. Yeah, so be careful with that. That's why they're separated. Remember, they're separated in a fuel cell. So be careful with that, with the wording here. So I would say C is the most possible answer for that. Hope that's right. So C. D, yeah, provide a surface for the hydrogen and oxygen to directly react together. They don't directly react together. So that's that. Question 13. The energy profile diagram below represents a particular reaction. One graph represents the uncatalyzed reaction and the other graph represents the catalyzed reaction. You should straight away look at the graph and you know which one's uncatalyzed. It's the one that has the highest energy, activation energy. In this case, it's this one over here. whereas the other one is, of course, uncatalyzed because it has a less activation energy. Whichever form best matches the profile diagram. So the activation energy for the uncatalyzed reaction is what? So remember, this is the uncatalyzed, the old big one. And what is the activation energy? It's this energy here, which is 90. And remember, activation energy is always positive. So it's 90 positive. So it cannot be A or C. Change in H for the catalyzed reaction. Okay, you don't have to worry about change in H. Change in H for both uncatalyzed and catalyzed reaction, it will be the same. In this case, what is it? We can see that it's exothermic, and it's from here to here. So from the reactants to the energy of the product, which is negative 50. Choose D as your answer. And the question for the complete combustion of methanol is here. The change in H for this combustion would be what? Easy. So we can see that there are two, remember the coefficient, there's 2 moles of methanol. So what we do is just we go on our formula sheet and go down. Where is methanol? Look at here. So methanol, which is here, has 726 kilojoules per mole. Now, because here we have 2 moles of it, because we have to multiply by 2. So imagine multiplying that 2, that's going to be 1,452. And remember, it's negative because remember, it is a combustion reaction, and we know that the enthalpy change is negative. So be careful with that. So it will be D as your answer for that one. Not too bad. Nice. All right. Question 15. The following table contains the percentage composition by mass of nutritional value of some common food. Okay, so we have fish, and it has 0 carbs, 0%, okay, bread, cheese, and milk. Whichever following servings has the highest energy content? So 100 grams of fish. So if we had 100 grams of fish, so if we say, okay, let's look at first 100 grams of fish. If we have 100 grams of fish, imagine 100 times 0%. We'll have 0 grams for this. What's 100 grams times 0.08, which is 8%? So using 100 times 0.08, which is 8%. That's 8 grams of fish. And the other one should be 100 times 0.29. That it will be 29 grams. So we have those, and what we do is look at our formula sheet. So what is the energy content of, let's look at this. Here it is. So fats, oils, and proteins. So in this case, we have, 0 carbs, of course, so that's not going to be anything. But we have 8 grams of, fats and oils, so 8 times 37. Plus 29 grams of protein, which is times 17. And that will release pretty much, this whole food, 100 grams of that will release 789 kilojoules of energy. Okay, let's do that for the other ones too. So in this case, bread, which we're using 80 grams. So again, what is 80 times how much percentage of carbs we have? So times 0.5, so that's 50%. So we'll have 40 grams of carbs. And so what's 80 times 4% of fats and oil, which is 0.04? That will be 3.2 grams. And what about 8 grams of protein? So 80 times 0.08. That's going to be 6.4 grams of protein. And yeah, now do the same thing. So if we have 40 grams of carbs, 40 times 16, plus 3.2 grams of fats and oils, which we times it by 37, plus 6.4 times for protein, which is 17. And that gives us an energy 867.2 kilojoules. So eating 80 grams of bread gives you much energy. What about 40 grams of cheese? Same thing. So 40 times how much percentage of carbohydrates? So 0.01. That's going to be 0.4 grams. So again, so 40 times 0.34. That will be 13.6 grams 40 times 25, so 0.25, my apologies, which is 10 grams. So let's, again, calculate how much energy. So 0.4 grams times how many carbs are? 16 plus 13.6 of fats and oils, which is 37, plus 10 grams of protein, which is 17, times by 17. That's going to give us an energy content of 679.6 kilojoules. And lastly, 258 grams of milk. So again, 258 times 5%, so 0.05. That gives me 12.9 grams. All right, so 258 times 4% fat, so 0.04. That's going to give me 10.32 grams. And 0.03, so we have 3% of protein, which for 258, we will have 7.74 grams. And again, do the same thing. So we have 12.9. It's such a long method, but yeah. So 12.9 carbs, which is 16, plus 10.32 fats and oils, which is 37, plus 7.74 times protein, which is 17. And that gives me 719.82 kilojoules. So the question tells us, what is the highest energy? Well, let's have a look at this again. Well, the highest energy is bread, as we can see. So choose B as your answer. Question 16. A silver oxide zinc battery is rechargeable and utilizes sodium hydroxide solution as the electrolyte. The battery is used as a backup in the spacecraft. If the primary energy supply fails, the overall reaction during discharge is this. When silver oxide battery is being recharged, the reaction at the anode is what? So anode is where, again, oxidation occurs. So let's look at discharge first. So what's going to happen? Well, just by looking at this, let's look at zinc first. So zinc is initially here, and it goes to zinc, zinc O. You can really do this quick, but I really want to show you how to understand how I write these equations. So zinc, okay, because remember it is a solution of sodium. The electrolyte is sodium hydroxide, which is a basic solution. So we can only add OH minus and H2O. So if we have one oxygen here, we need to put another oxygen here, which I'm going to put OH minus. Now, both are not equal because we have hydrogen here. So if I add H2O, and if I make this 2, are they equal now? So we have two oxygen, great. 2 hydrogen. Yes, now they're equal. Now let's look at the overall charge on the left. The overall charge here is this one 0, whereas this one has -2. Remember, -1 times 2, so we have a -2 charge over here. Whereas here, this one has 0 and this one has 0. So the overall charge here is 0. How do we make them equal? By adding electrons. We have to add electrons to the right, especially 2 electrons. If you add 2 electrons, imagine -2, because -1 times 2, so 0 minus 2, which is -2. Both are equal now. So what is that? Well, okay, means the zinc is, what is it going through? It's going through oxidation because the electrons are on the right. There we go. So let's look at the Ag now. So we went from Ag to O, and it went to 2Ag. Okay, so what do we know? There is an oxygen here, so I'm going to pretty much put an OH here minus here. And now we have a hydrogen, so I'm going to H2O here. I'm going to put a 2 here. And pretty much they're equal now. So the overall charge is here 0, whereas here it's -2. So we have to add 2 electrons on the left side to make them equal. So give them my overall charge. So this part here, what we can do is bring this over here. Plus 2E minus. Perfect. So we both have our, what we call the oxidation reaction for the discharge and the reduction reaction for the discharge. And what happens when they recharge is they just swap. So for example, let's look at recharge here. So it's going to be, imagine like these, the products are going to be, you know, like flipped around. So it'll be zinc O plus H2O plus 2E minus goes to zinc plus 2OH minus. So now what's happened? Well, now the zinc has gone through reduction and the Ag has gone through and now the Ag has gone through oxidation because the electrons are on the right. And that's what we want. Remember, anode is where oxidation occurs. So in this case, it will be A. You could have done this easily, I'll be honest. You could have done this faster, but I do want to show you how we calculate them. For example, how to look at it deeply, how to write an equation properly. And yeah, so the fastest way you could have done it is like in a real exam. In this case, you would have done this. So a hint. Okay, this one has a oxidation number of 0 because it's just zinc. And here now, it should have a positive 2 because remember, this one would have a negative 2 here. So if that's so what's happened? We went from 0 to plus 2. So what's gone? The oxidation number has increased. So the way we compensate that is we put 2 electrons on the right, meaning that it's gone through oxidation. If this has gone through oxidation, then this one has gone through reduction. And remember, what happens is when you swap them around, when they recharge, if this one is gone through reduction, it will swap around. So pretty much this will go through reduction, then, and this one will change to oxidation. Yeah, this is a quick way. You can just use oxidation numbers, but yeah, in a real exam, you use oxidation numbers, but I do really want to show you how to write these equations. So yeah, that's it. Move on, next question. Okay, so for 17 and 18, so a clear colorless liquid extract of rhubarb plant was analyzed for the concentration of oxalic acid, but direct titration with recently standardized and acidified potassium permanganate solution, which is this. The balance equation for the titration is shown. All right, so let's have a look at it. So we have, of course, this is our concentration of oxalic acid, and this one is our potassium like this. It's this, yeah. The steps in this titration were as follows. 20 milliliters of alicate of the rhubarb extract was placed in a 200 milliliter of conical flask. The burette was filled with acidified 0.02 mole, standardized solution of this. The acidified 0.02 solution was titrated into the rhubarb extract in the conical flask. The titration was considered to have reached the end point when the solution in the conical flask showed a permanent change in color to pink. The volume of the title was recorded. The titration was repeated until 3 concordant results were obtained. The average of the concordant titers was this. The concentration of H2C2. So what's the concentration of oxalic acid of the rhubarb extract is? Not too bad, nice and easy. So, if we know the concentration of, the standardized solution in this case, which is KMNO4, 0.020 mole. Molar. And we know that the volume of the titers, the contorted titers, which is for the standard solution, is 21.7 times 10 to the negative 3 liters. Make sure it's in liters. And we can actually find the mole. Remember, N is equal to a concentration times, the volume. So the mole of KMNO4, which is the same as the mole of this one over here, remember? So we can rewrite this as just MnO4 minus is what? It's going to be these two multiplied. So let's do that in a calculator. 0.02 times 21.7 times to the negative 3, which is 0.000434. And now we have that. Now, of course, we're going to use ratios to find the concentration of this. So to find the mole of C2042 minus, it's going to be this. Times is what we're trying to find out. It's this. What's the coefficient? It's 5. Oopsies. 5 divided by what's the coefficient of what we just used here, which is 2. It's 5 over 2. So times that by 5 over 2. And that gives me N pretty much is 0.00185. And remember, we want to find the concentration. Remember, what is the concentration? It is going to be, remember, N is equal to CV. So N over V is equal to the concentration. So we know the number of moles, luckily, and we know the volume of the allocate in this case, which is 20 milliliters. So it will be 0.001085 divided by the volume, which is 20 milliliters. So 20 times 10 to the negative 3. Which gives us 0.05425, which looks like A is your answer. Nice and easy. Beautiful. So I'm going to make this smaller. Oops. Why am I not? All right, this is really annoying me. I'm going to put it right over here. Okay, next question. Which of the following rinses is least likely to affect the accuracy of the result? So we don't want to affect the accuracy. A, let's look at A. Burette. So the item is the burette and its rinsed solution is distilled water. No way. Don't ever do that. Burette is rinsed with the standard solution, which in this case should be rinsed with KMNO4. So distilling with just decreases the concentration of that. Yeah, so this will affect the accuracy highly. The burette is rinsed with the rehoboth extract. No, remember, it's rinsed with the solution, the standardized solution. So be careful of that, not that. Pipette, so it's rinsed with KMNO4. No, don't do that. Remember that this will affect, the accuracy, of course. When you don't want to use that. So normally with the pipette, you want to rinse it with the actual, the allocate, which in this case is the oxalic acid. And D, conical flask, distilled water. Yeah, you can. Yeah, you remember the conical flask? Normally, it makes sense because remember, sometimes what they do is they dilute it. For example, if you have a 20 milliliter allocate and sometimes they dilute it, so it creates the dilution factor, you can actually put water in that conical flask and it really doesn't affect the concentration. It actually has no effect. So the conical flask, yes, you can rinse it with distilled water and it really wouldn't affect it. So D would actually have no effect, the least effect in the accuracy. Question 19. Which of the following molecules contains a chiral carbon? Remember, a chiral carbon is when you get a carbon that has 4 different side groups. So let's check this first one out. So it's a double bond. So CH here. So the first one is H here. H here. H here is C. Okay, so we have this, and well, none of them actually have. This one has. These are all the same. This carbon here has the same as these ones. This one over here has only. It has this one. So remember, you cannot have a double bond. When it's a double bond, it doesn't actually. It's not chiral. So, A looks very wrong. So A is wrong. Let's check B. So it's a CF here. H, C here, and Cl. Well, here, this carbon it has these are the same, so that's wrong. These are also the same for this carbon. And this one, it has 2 hydrogens that are the same, so no. Let's check the next one. Next one is that OH group. C and a CH through here. Let's check this one. This carbon actually does have, look, it has a hydrogen here as this whole group here on the other side. So it's a ethyl group. It has a methyl group, totally different, and it has a OH. Yes, it has 4 different side groups. So C looks great. So I'll choose C in that one. 20. The kinetic energy of a sample of gas in a container of fixed volume is represented by the distribution curve as shown in graph 1. So, okay, we started with graph 1 in other words, yeah? One change was made to the sample and the resulting distribution curve of kinetic energy is shown in graph 2. So they've made an energy. You should know this is a Max-Boltzmann graph. And what do we know? We know that when, for example, if you look at this curve over here, if it's like this, the temperature is quite low. And as you increase temperature, what happens in the Max-Boltzmann graph? It spreads pretty much. So what do we know? We know graph 1 has a higher temperature. So graph 1, temperature was high, temp. And so in graph 2, what they've done is they've decreased that temperature. Which of the following statements explains the change from graph 1 to graph 2? The average kinetic energy of the gas molecules decreased. Yes, remember, whenever you hear the word average kinetic energy, it's all about temperature. So if the average kinetic energy is decreased, it means the temperature had been decreased, which is true. If we're going from graph 1 to graph 2, yes, we can put a tick on that. More gas at the same temperature was added. No. That 100% that the temperature was pretty much decreased. But the way you actually see that is, okay, look at the mean. The mean of this one over here is, this is your kinetic energy. Remember, this is kinetic energy. Let's say, I don't know, it's like 20 here. That's your mean. It means your average kinetic energy of all the molecules. And then the average kinetic energy, let's say, of graph 1 is, let's say, 40, because remember, it's on the right. So what can we see? Of course, the average kinetic energy of graph 1 is much, like the mean average kinetic is much larger, means that the temperature of this one must be higher. So, yeah, so in other words, we don't... so more gas at the same temperature was added to the kinetic. No, that's rubbish. More collisions occurred between the gas and particles. No, because the temperature has been decreased, there is less collisions that are going to be acting. So C is wrong. The temperature of the gas was increased. Rubbish, it's been decreased. So A is your possible answer. Nice and easy. Question 21. A student wants to use a physical property to distinguish between two alcohols, octane 1-ol and propane 1-ol. Okay, so we know octane has 8 carbons, whereas propane has 3 carbons. Both alcohols are colorless liquids at standard laboratory conditions. The students should use what? Density? Because propane 1-ol has a much higher density than octane. Rubbish. The more higher the carbons are, the more denser it is. Octane 1-ol is much dense than propane 1-ol. So it said density because propane 1-ol doesn't have a high density. Octane 1 has. Boiling points, because octane 1-ol has a higher boiling point than propane 1-ol. That's true. Remember, the more higher the carbon chain is, in this case it's octanol, it will have a higher boiling point, because remember, both have hydrogen bonding and dispersion forces, because octane 1-ol has a larger carbon change, it has much stronger dispersion forces. So B looks quite good, so we'll put a tick on that. Electrical conductivity, because octane 1-ol has a higher conductivity than nothing. It's no, they're not conductive. These are not conductive, by the way. Actually can. They're not very conductive, in other words, because remember, so they're not very conductive. B, spectroscopy, because it is not possible to distinguish between the alcohols using their physical properties. Wait, spectroscopy, because it is not possible to distinguish between alcohols using their physical... Yes, you can. We know octanol has a higher boiling point, so, and propane 1 has a lower, so we can actually distinguish that by physical properties. For example, we can burn which one would likely to melt or has a higher boiling point. So we can actually use the boiling point to distinguish those physical properties. So B is the most possible answer for that one. Question 22. 4 fuels undergo complete combustion in excess oxygen, and the energy released is used to heat up 100 grams of water, okay? Assuming there is no energy lost to the environment, so which of these fuels will increase the temperature of the water from 25 degrees Celsius to 85? So let's actually find that change in temperature. It's actually 60 degrees Celsius, the change in temperature. So let's find out how much energy this releases. So 0.889 grams of hydrogen gas. Let's look at our data book. So hydrogen gas is here. This is hydrogen gas. Because we have it in terms of grams, we're going to use this one over here. So what's 0.889 times that 1 for 1? So it's actually going to release 125 kilojoules of energy. And so be careful. Remember, we're going to times it by 1,000 to make sure it's in joules. And so now we have the energy, which is 125,349. We're going to have to use energy is equal to MC delta T to find that delta T. And if that delta T is 60 degrees, that's the fuel. So in this case, delta T is going to be the energy, where the mass is, I think, was it how much? 1,000 grams of water times 4.19, 4.18. So 4.18, and that gives me 30 degrees Celsius, the change in temperature. That's wrong. We want 60. So I'm just going to keep doing this for all of them. So the next one is 3.95 grams of propane. So where is propane? Propane's here. So, and we have it in terms of grams. So I'm going to multiply with this. So 50.5 times how much? What's the mass? So 3.95. And that's going to release 199.475 kilojoules. We're going to multiply by 1,000. And then so it's 100 times 1,000 times 4.18. And that's going to, what's the energy change? It is 48 degrees. That's also wrong. Oops. Next one, methane. And we have 0.28 this. So methane, where's methane? This is methane. Because we have it in terms of mole, we're going to use this one. So it's 890 times 0.282. And that gives me 250 kilojoules. So I'm going to times it by 1,000. And then what's 1,000 times 4.18? That gives me a change in temperature of 60 degrees. Perfect. Your answer should be C. Done. So it's the actual, yeah, it's methane. 22 is C. Nice. Question 23. A student is asked to research and then recommend either petrodiesel or biodiesel as the preferred fuel for a small Victorian transport company. The company stores some of its fuel supplies in tanks situated in a remote location for occasional use. The air temperature in these remote locations can range from 0 degrees Celsius to 40 degrees. Quite good. I mean, it's not very, very cold, so it's like great temperature. Remember, we know when biodiesel is a problem when at cold temperatures because it has a high viscosity. And it's hard for fuel lines. So yeah. Based on this information, the student will recommend petrodiesel rather than biodiesel because what? And well, in this case, actually, the temperature is it's 0 degrees Celsius to 40 degrees Celsius. So it's still a problem for using biodiesel in terms of that 0 degrees Celsius because if it goes that low, it's a problem for biodiesel because it will be hard for it to go through fuel tanks. So so the student would recommend petrodiesel rather than biodiesel because petrodiesel what? We know petrodiesel has a low hygroscopic. Remember hygroscopic is like it likes to suck water in, like it just likes to take water in. We know because petrodiesel doesn't like water because it is mostly nonpolar and it's actually it's fully nonpolar. It doesn't actually so it doesn't go for water, whereas biodiesel does. So we want to take A and B wrong. So it's less hygroscopic. And petrodiesel is also less viscous. Remember, biodiesel is highly viscous. So it looks like just D is your answer in terms of that. Less viscous. So 23 is D. Next question, 24. The four equations below represent different equilibrium systems. Okay, we're given here. After equilibrium was established in each system, the temperature was decreased. So we have temperature decrease and the pressure was increased. So pressure increase. In which equilibrium system would both changes result in an increased yield? Remember, whenever you hear the word yield, it's look at the product side. So for the products here, which one will increase the products? So that will increase the yield. Let's look at the first one. Because it's an exothermic reaction, remember we're going to put energy on the right. Remember, because there's energy going to be released from the out. And so if we are decreasing temperature, we're decreasing that energy. Imagine, okay, we decrease that temperature and the system's like, wait, I need to increase that temperature. I need to increase that energy. So it's going to shift to the right. And guess what? If it shifts to the right, we increase the yield of our products. Great. So it works for this equation one. What about pressure? So let's think about pressure. If we increase pressure, the system's going to, wait, That's too much pressure. We want to decrease that pressure. And for it to decrease the pressure, it's going to go for the side that has the lowest molecules. For example, this has 2 molecules and this one has 3. So it's going to go to the right, which is great because if it goes to the right, we get more product, which is our yield. So I think it's just equation 1 in this case. I'll say equation 1. Let's try to look at equation 2 too. So, okay, it's still exothermic, so I'm going to put energy here. So imagine decreasing energy, it will increase the yield. That's okay, that makes sense. So hence, for the other ones, because they're endothermic, they are wrong. Because endothermic, yeah, they will shift to the reactant side. What about pressure for this one? Say, okay, we increase pressure and the system is like, okay, we need to decrease that pressure. So it's going to go to the less reactant side. So both sides have 2 here and 2 here. So it's not going to go either way. So the only, pretty much equation 1 is your best answer there. 25. The molar heat combustion of propane 1-ol is this, is that. And we're given the molar mass of that. The mass of this in tons. So tons is, remember, it's 1,000 kilograms. Required to produce 10,800 megajoules of energy is closest to what is what. Okay, so what I would do here is, okay, if we have 10,800 megajoules, now mega, we can write it as 10 to the power of 6 because it's like a million, yeah? Joules, we can write it as that. We want to convert it to kilojoules. So the way we do it is we just divide it by 1,000. So let's do that. So that will convert it to, so what's 10800 times to the power 6 divided by 1,000. That gives me 108,000,000, oh my god, kilojoules. Now remember this here. So this is we can make an equation from that. So 3329 is equal to kilojoules per mole. So kilojoules per mole. Because we have the energy in terms of kilojoules, so we can sub pretty much this stuff in here. We just need to calculate how much mole. So that divided by 3329, that's going to give me the number of moles C5H11OH, which is 3244.217 mole. Now we want the mass. So the mass is easy. It's just mass is equal to the number of moles times the molar mass, which is 3244.217. The molar mass, luckily they've given it here, it's 88. Times 88, and that gives me, in terms of grams, it gives me actually, I'll rub this whole thing off. It gives me 285491.1385 grams. Of course, we're going to divide it by 1,000 to get it into kilograms. Which is 285.491. That's in kilograms. Remember, in terms of tons, we're going to divide again by 1,000. Because remember, 1,000 kilograms is a ton. So imagine dividing this by another 1,000. That gives us, in terms of tons, 0.285 tons. Answer B. Done. 26. Organic acids, including vitamin C, so ascorbic acid, are present in lemon juice. Since organic acids and vitamin C are weak acids, so, okay, weak acids, they will undergo acid-base reactions, okay? Only vitamin C, not the organic acid, will undergo a redox reaction with iodine. So only vitamin C will go through a redox reaction with iodine, but not the organic acids, okay? Which of the following methods would be most appropriate to determine the concentration of organic acids and the vitamin C in a sample of lemon juice? Well, here they've given us, okay, well, the best way, organic acids including vitamin C are present. So remember, so a vitamin C is an actual organic acid. So the way to determine the organic acid, like the concentration, is how we can go through acid-base type reaction. That's going to help us to, find the overall organic acids, which will include both the vitamin C. So that'll be great. So, well, here they're also saying titration. So yeah, an acid-base titration to find the concentration of organic acid. But then we also want to find the concentration of vitamin C in that lemon juice. And remember, they've given us a hint. Only vitamin C, not all like the organic acids will undergo redox reaction. So only vitamin C will go through redox reaction with iodine. So another way we can actually determine organic, the vitamin C concentration is going through a redox reaction. So let's look at, hey, an acid-base titration with sodium hydroxide and phenolphthalein acid. So, okay, the acid-base titration works because it will give us the concentration of the organic acids. But what about vitamin C? They haven't talked about, remember, they're talking about also vitamin C and the vitamin C. So they haven't talked about redox reactions in this case. So that will give us the overall concentration of all organic acids, pretty much, OA, all organic compounds, but it doesn't actually give us the vitamin C concentration. And B, an acid-base titration with ammonia. Okay, be careful here. They're telling us it's weak acids. What do we know about titrations? Weak acids, the way we go through titration is we have to react it with a strong base. If it's the other, even vice versa, if you have, for example, a strong base, so strong acid, we always react it. We want to also react it with a weak base to find the equivalence point. So in this case, using ammonia is a problem because ammonia is a weak base. So if you're using a weak base on a weak acid, it's not going to be a great way to determine the concentration of the actual concentration of organic acids. An acid-base titration with sodium hydroxide. Beautiful, look at that. Sodium hydroxide, what do we know? It is a strong base. So we know a weak acid plus a strong base, so that's going to be good. And methyl orange, so methyl orange indicator. So, okay, we know weak acid. Let's say weak acid is like what? I don't know, like let's say it's 6 pH, yeah? The pH is 6. Because it's going to be, it's an acid. So it's below 7, but it's weak, so it's around 6. And then, you're adding a strong base, so it's going to increase it. So imagine like it increases to like 8 or 9 or like around, I don't know, 8 to 10, I would say, the pH. So if we use a methyl orange indicator, let's look at the methyl orange indicator using our data book. Is it a great indicator to help us look at that? Let's check that. Let's see the range here. So remember, we're looking at the range at like, 8 to 10. So these are the best ones we would want to look at. So where is methyl orange? Where is methyl orange? No, methyl orange is here. It's not over here. So it's not it's very bad because it's used for acidic, highly acidic pH ranges. So that's not the best one. So choose that. Is not right. Next one, an acid-base titration with potassium hydroxide. Again, potassium hydroxide is great because it's a strong base. And phenolphthalein, which is great. It's right over here. So that is great. It's one of those. And let's look at it. And a redox titration with iodine and starch indicator. That's great. Remember, to find the concentration of vitamin C, it has to go through a redox reaction. Yeah, and they've done that. So D is the best solution here. Wow. I hope that's right. Yeah. So 27. So we have a reaction and we have the Kc value, 150 degrees. Given that the information was, what is the Kc value for the reaction this? What they've just done is, okay, let's find the Kc value of this. So the Kc value is IBR squared, all divided by BR2 I2, and this value here, what is it? It's equal to this Kc value. So, and then what they've done is they've reversed the reaction and they've doubled it. So, for example, if this is your Kc value, they've pretty much twisted it around. So, for example, they've took this, they put this on top, and they've put this at the bottom, and they've so what would if you're gonna like reciprocate it, it's gonna also, this one's gonna reciprocate, and then they've also squared it. So if that's squared, and this is to the power 4, this is also going to be to the power, squared. So it's going to be 1 over kc squared. Yeah. And you can and it makes sense, because like you find the kc for this one is what? Like it'll be br2 squared, I2 squared. As you can see, it's the same as what we've done here. All IBR to the power 4. It's the same as that. So that is our equation that we're going to use. So it's going to be 1 over, what's our kc, which is this? 1.2 times 10 to the squared, and squaring that, that's going to give us our new kc value. Which is 0.00069, which looks like C is your answer, because it's 69 here. So, yeah, 27C. Next question. Which of the following is a dipeptide made from an alpha amino acid? All right. And dipeptide. I think the way that I would do this one is, okay, so where is the polypeptide linkage? For this one, it's here. This one is over here. This one's over here. This one's over here. And let's look at what are the, like for example, let's look at A. Remember, we have the list of the alpha amino acids. So in this case, like if you go down here, for example, here, what do we have here on top of this? We can see that we have a CH, carboxylic, and it has, what is the, like the, yeah, that group, it's a CH3. So which one would it be? It would be this one. As you can see, this here is bonded with that. And that CH here is this CH. And this is that. So it is going to be, and as you can see, the R group here is the same as this R group. So yeah, this here is great, because this part here, remember, these all of these are an actual alpha amino acid. So yeah, so this one is alanine, so that is great. This part here is alanine. What about the next part here? What is this? Well, they have a CH2 bonded. CH2 bonded. Do we have something like that? That's, yeah, that's, so CH2, where is that? There is no, so we have here CH2. But no, it's not the same as that. CH2. No, it doesn't actually. Yeah, this one is wrong. Be careful. This, we don't have a CH2 here. If it was this part over here that was here, then it would be right. But yeah, that doesn't. This is not an actual in any part of these amino acids. So that's wrong. What about the next one? Let's look at this part here. So this part looks like this part over here, great, which is glycine. So when, yep, and the next part is, what is it? So, okay, so he has a CH, so I'm gonna, okay, which one has CHs? Okay, this one has a CH, and what else? So this one and this one, but this one has just an S, so pretty much that's the only one. So if I know that this one has a CH, is it that one? So it's this carbon. Nope, that's absolutely wrong. As you can see, this carboxylic acid is over here, and this is the CH, which is this one. And then it's supposed to be amino acid, but it's this one over here, which is rubbish. So B is not your answer for that one. Next question. So we can see it's CH here, which is it the same as that one? CH here. Yes, it is. This one actually is great. So it is cysteine. What about this part over here? So remember, it has an S. So which one has an S here? Where was it? Here, this one. Great. So this one has S here, as you can see. So let's check if that makes sense. So amine here, so it has a CH, and that's a CH. This one is here. That, and that. Yes! So 28 is C. Pretty much it has all of those. So I would say, yeah, 28 is C. That's how I would do this question. Pretty much, yeah. That's it. Next question, 29. The following diagrams represent combinations of 4 galvanic half cells. So we've given these that were investigated under standard conditions. Each half cell is consists of a metal electrode placed in a 1 ml nitrate solution of the respective metal ion. The diagram below shows the polarity of the electrons in each half cell reaction as determined using ammeter. The results were then used to determine the order of the E0 values of these half reactions. Whichever form indicates the half cell reactions from the lowest E value to the highest. Now you should know that the highest E values, like when you look at these, the highest E values are where? Now normally this question is it's always in many exams, like practice exams and the old practice exams. So always remember, okay, we know that the highest E values and the lowest E values, like imagine, yeah, those highest E values are what? They're the strongest reducing ones, which are the strongest oxidant. And the bottom ones is what? It's the one that goes through oxidation, which are the reductant. So the highest E values are the strongest reducing. So in this case, and we know that the highest reducing, because this is galvanic cells, the ones that are being reduced have a positive polarity, and the ones that are going through oxidation have a negative polarity. For example, if this one over here has a positive polarity, so it would be, so G, let's write G here. And because it has a high polarity, it's on top. And this one has a negative, so it means it's at the bottom. So Q has to be at the bottom of G. Because remember, in terms of this, we know G is top because it's stronger reducing, so it's stronger oxidant. Hence, that's why it's positive, and this one's going to be negative. So we're going to put G here, and we're going to put Q here. Great. Now let's look at the other reaction that can help us. So actually, let me put this here. Yeah. And the next one is it's saying that Q is positive. So remember, if Q is positive, again, so if Q is positive, so it's top, then J. So Q is top, then J. So J has to be bottom of Q. And that makes sense because Q is a stronger oxidant. So that's why it's positive in this case. And then let's do the next case, just J here. So J is positive in this case. So J is going to be on top, then R. So R is going to be at the bottom in this part over here. R is going to be at the bottom. So in terms of the strongest oxidant, it'll be, G, and, as it goes down. And the strongest reductant is going to be from R on top. So let's look at the question. Oopsies. Which of one indicates the order of the half cell reactions from the lowest E, these values, to the highest? So remember, this is the lowest. It's at the bottom. It's the lowest to the highest. So they go from R, J, Q, and G. Which looks like C is your answer, that one. That was easy, actually. That's nice and easy. And the final question. In the human body, not all energy available for the metabolism of food is dissipated as heat energy. A student carried out further research on this and found that some of the energy is used for the production of adenine triphosphate. You would know this. This is ATP. If you do biology, it's the most used up from adenine diphosphate and inorganic phosphate, according to his following equation. As we can see, so we have adenine diphosphate, and it reacts with a inorganic phosphate, and that kind of comes together and it creates adenine triphosphate. So perfect. What do we know about this? About this reaction, because we're gonna have, of course, put some energy. You have to put some energy to put phosphate and adenine triphosphate. You're gonna put some energy to make them actually put together to make ATP. So it is what? If we're putting energy, it absorbs energy. So it's probably an highly endothermic reaction in this case. The student also learned that the overall equation for the aerobic, remember aerobic means that it uses oxygen. Respiration can be represented as shown. Okay, glucose, oxygen. So we have ADP, phosphate, some hydrogen ions. So okay, that's good. Let's look at the question. It is reasonable to deduce that an aerobic respiration, the formation of ATP is a hydrolysis reaction. Wrong. This is condensation. When you're creating ATP, as you can see, water is the byproduct. Whenever water is the byproduct, it is a condensation reaction. If it was a hydrolysis, water would be used on the reactant side. So, wrong. For 3.3 grams of CO2 to be produced, 0.4 moles of ADP is needed. Let's check that out. So, if we can find the mole of CO2 first, which is the mass, which is 3.3, and the molar mass they've given us, which is 44. So that's 3.3 divided by 44, and that's going to give us 0.075 mole. And we want to find the mole of ADP. Now, the number of moles of ADP to minus is what? Well, where is ADP? ADP is over here. So it's 32, the coefficient. And which one did we use? CO2, the number of moles of CO2, which is 6. So what's that? Times by that. So 32 divided by 6. That gives you 0.4 mole. Beautiful. That actually works. So looks like B is your answer for that one. Let's look at the next part. The production of ATP 3- from ADP and PO4 is an exothermic reaction. Wrong. Remember we said it was endothermic. So yeah, the oxidation of ATP. We're going to need energy. The reaction actually absorbs energy. 9.5 grams of glucose will produce 2 moles of ATP. Okay, so again, same thing. So find the moles of glucose. So I'm going to write glue. This is fast. So it's 9.5 divided by the molar mass, which they've given us is 180. Number 5. 180. 0.05277 mole. And I want to find the mole of ATP, which is what? So 0.05227, times, where's ATP? ATP has 32 as the coefficient. And what am I using? I'm using glucose, which has a 1. So imagine times that by 32. That gives us 1.68 mole, which here has 2 moles, and that's wrong. So the only possible answer is B. And that's it, guys. I hope you guys learned something through this video. Please make sure to like and subscribe for more future videos like this. And take care of yourselves. Bye-bye.